Hey everyone, welcome back to another Explainer. Ever wonder how millions of people can stream the exact same Super Bowl broadcast at the exact same time without, literally breaking the internet? Well, today we are unpacking the absolute magic behind it. It's a truly fascinating look into the invisible plumbing of our digital world.
So here's our roadmap for today. We're going to look at the video streaming problem, why multicast is the perfect compromise, how we build multicast trees, crossing network borders, the SSM evolution, and finally, the hardware that does all the heavy lifting.
All right, let's kick things off with Section 1, the video streaming problem. To really wrap our heads around the solution, we kind of have to look at the problem first. Imagine you've got a local network with, say, 100 users, right? And a server needs to send a live stream to just 20 of them. If we use unicast, which is just your standard one-to-one traffic, that server has to send out 20 individual streams. That eats up a massive amount of bandwidth. On the flip side, if we use broadcast, the server only sends the stream once to the entire subnet. Sounds better, right? Well, not really, because now the 80 devices that didn't even ask for the video are forced to inspect and drop those packets, which puts a huge unnecessary processor burden on them.
Which brings us to Section 2, Multicast, the efficient compromise.
So as you can see, neither unicast nor broadcast really scales for live video. I mean, you can't duplicate a stream a million times, and you definitely can't just broadcast it to the entire internet. So enter multicast. Think of multicast as this highly efficient, totally dynamic delivery service. It uses a specific range of addresses. These are known as Class D IP addresses, ranging from 224.0.0.0 all the way to 239.255.255.255. Basically, a server sends just one single copy of a packet into the network, and it's delivered only to a dynamic group of destinations that actually requested it. The routers and switches do all the hard work of replicating that packet, but only at the exact points where the paths to subscribers actually split. This gives us a brilliant look at what a multicast tree actually looks like in action. You've got the video source over there on the left, sending a single stream out to the multicast IP 239.1.1.1. Now, as that stream hits those routers and switches, notice how it only duplicates the packets exactly where the path splits to reach an active subscriber. The non-subscribers, they see absolutely zero traffic. It's incredibly elegant.
And here is a fun little fact for you. This isn't just network theory. You can actually ground this concept in reality. If you're sitting on a network that's actively streaming multicast video, you can open up a program like VLC Player, select Open Network Stream, and literally intercept a UDP multicast stream. You just punch in the address, something like UDP:///239.255.9.50 port 1234, and assuming your network interface has the right multicast routes, boom, the video will just pop right up on your screen.
Okay, moving on to Section 3, building the multicast tree.
Now, you might be wondering, how on earth does the network actually know who wants to watch the video? Routers aren't mind readers, right? Well, think of this process a bit like setting up a newspaper delivery route. First, you have IGMP, or Internet Group Management Protocol. This is essentially your last mile protocol. The receiver basically raises its hand and tells its local router, hey, I want to subscribe to this channel. Then we have PIM, which stands for Protocol Independent Multicast. This is our core protocol. PIM takes that local request and builds the delivery route backward through the network all the way toward the source. And to make sure traffic doesn't get caught in some endless catastrophic loop, it relies on something called Reverse Path Forwarding, or RPF.
So here we can actually see that exact translation from the client to the core. On the right side, the receiver is using IGMP to tell router 3 that it wants the stream. Router 3 then uses PIM to fire a join message back through those core routers toward what we call the rendezvous point, or RP. And notice those RPF checks in action. Multicast basically piggybacks on the unicast routing table to ensure it only accepts multicast packets on the interface that is the absolute shortest path back to the sender. If a multicast packet shows up on the wrong interface, it's instantly dropped. And that is exactly how we avoid massive broadcast storms.
Let's zoom out a bit for Section 4, Crossing Network Borders.
What we just looked at works beautifully if you're inside a single company's closed network. But the internet is obviously a massive collection of different autonomous systems, and that poses a major challenge. A network domain owner, let's say a major internet service provider, wants to secure and control their own rendezvous points. They definitely do not want to share their RPs globally with other providers. So if a receiver in domain A wants to watch a stream from a source all the way over in domain B, how do their respective RPs actually find each other? Well, to solve this little puzzle, network engineers introduced MSDP, or Multicast Source Discovery Protocol. MSDP essentially sits right between the two domains. It allows the rendezvous point in domain 1 to quietly whisper across the border to the rendezvous point in domain 2, basically saying, hey, just so you know, I have an active source sending video to group G. Once domain 2 knows that source exists, its receivers can finally build a path over to it.
And this is where the real heavy hitter steps into the ring. MPBGP. MPBGP is an extension of the Internet's core routing protocol, and what it does here is absolutely crucial. It keeps a totally separate routing table just for those multicast RPF checks. Because remember, network administrators often want multicast traffic to take a completely different physical path than regular unicast web traffic. So MPBGP provides the map, and then PIM, SM, or sparse mode, follows that map to create a shared multicast distribution tree across the different autonomous systems.
All right, that brings us to Section 5, the SSM evolution.
Honestly, managing all those rendezvous points and running MSDP across different global domains, it's a huge administrative headache. So enter Source-Specific Multicast, or SSM. The big takeaway here is that with modern services, like Netflix live streaming or cable TV over IP, the receiver already knows exactly who is sending the video. We really don't need a middleman rendezvous point to figure out where the stream is coming from. Because we know the source right up front, SSM simplifies the whole shebang. It completely eliminates shared trees, gets rid of RPs altogether, and entirely removes the need for MSDP.
You can really see here how this builds a vastly superior, much cleaner architecture. SSM creates an optimal, shortest path tree directly from the receiver straight back to the source. The receiver uses IGMP version 3 to say, hey, I want group G and I specifically want it from source S. MPBGP still handles those interdomain routing checks, but the tree builds straight through. It is a real game changer because it vastly reduces administrative overhead and memory state on those core routers.
And finally, Section 6, hardware that does the heavy lifting.
Up to this point, we've really only talked about software. But look, protocols are just math and ideas, right? In the real world, it takes actual physical brawn, custom silicon chips, to replicate millions of packets in real time, 20 gigabits per second. Just think about that. That is the massive amount of replicated multicast traffic a single physical ASIC, specifically Cisco's Janus chip, which you'd find on their 7600 series line cards, handles entirely on the fly. When a packet comes in and needs to immediately go out 50 different ports, it's not the main CPU doing that work. It's this dedicated, highly specialized hardware, copying those electrons at literal lightning speed.
And it doesn't stop there. These supervisor engines can perform up to 25 million packets per second lookups centrally. To put that into perspective, this dedicated hardware is absolutely vital because if the router's main CPU had to process all these packets, it would cause massive, unacceptable delays. And in the world of digital video, delay and packet loss result in what are known as CC errors, or continuity counter errors. You know, when you're watching a stream and the picture suddenly blocks up, pixelates, or totally freezes? Yeah, that's often a CC error caused by a network just failing to replicate those multicast packets fast enough.
So, we've seen how multicast elegantly balances network bandwidth and processing power, acting as the invisible backbone of live digital broadcasting today. Through protocols like IGMP, PIM, and the super streamlined SSM, it builds direct, incredibly efficient paths across global domains. But it leaves us with a pretty massive question for the future. As live video streams push past 4K into incredibly data-heavy 8K and beyond, are these dedicated hardware ASICs going to be able to keep up with the replication demands? Or will the internet need to invent an entirely new compromise? It's definitely something to think about. Thanks so much for joining me on this explainer, and keep questioning how your digital world is built.